Well, thank you very much, Peter, and it is a great pleasure to be here today to talk to you and give this Bjerknes lecture. I asked if I could point at the screen, so this is the one I'll be pointing at, so you won't see a picture of me, but what I'm talking about, which I think is far better. So I'm going to talk to you about how air gets from one hemisphere to the other, and centered on the Hadley cell. And the talk then is joint with some people at Reading that I talk to quite frequently, and these days I'm totally unable to produce any results from data myself, so I have to rely on others to do that. So anyway, let's go on and just show straight away the zonally averaged circulation, and there we see our beloved Hadley cell. See if I can operate both of these. So I've got to slouch over so you can hear me still. So here's our Hadley cell here. This is for June to August, and we see the circulation with the rising where there's latent heat release, the descent where there's the cooling in the winter subtropics, and the motion from the winter to the summer at low levels, and the opposite in the upper troposphere there. And it's always very tempting with pictures like this to start waving one's hands, and that's fine, but if you start assuming that the air does that, then you can be in trouble, because it doesn't necessarily, and that's what I'm going to be talking about. Now, we also often hear about angular momentum conservation too. So if you think of angular momentum, I've written it down there, then following a parcel, then it changes because of pressure gradients, but in the zonal average, then it is actually, if there's in the absence of frictional forces, it would be conserved. But if you move the air, conserving angular momentum from one hemisphere to the subtropics in the other, you'd reach a jet which is about 4 times the strength of the jet we actually have. So clearly it's not that simple. Now, so I'm going to be discussing this, and pressure gradients changing angular momentum are always a problem. It's much easier to start dealing with vorticity. And the relationship between the two is that essentially the latitudinal gradient of the angular momentum is equal to the vertical component of vorticity. So if angular momentum is conserved, then the vorticity, the absolute vorticity, is 0. And that's the sort of thing that happens in the subtropics to a certain extent. So vorticity is good. Yes, I've lived a lot on vorticity, but as you guessed, really what I'm going to deal with is potential vorticity, because that then is conserved on a fluid parcel in the absence of diabatic and frictional processes. So I thought I'd give a little primer, which goes back to the paper Hoskins, McIntyre and Robertson that Peter mentioned, and already his bet's been won by the fact I've mentioned it. And so I'm going to give the NODI guide. Does NODI work in the US? I'm not sure. Anyway, the NODI guide to potential vorticity. And never be phased out by it. All it is you think of a cylinder between 2 isentropic surfaces. You have the circulation around that cylinder, represented by the normal component of vorticity, and the separation of those 2 isentropic surfaces. And if it's adiabatic and frictionless, then that is conserved following the motion. Apart from the density, which is a small effect here, it really is the vorticity divided by the separation of the isentropic surfaces that is conserved. So that then encompasses some of the things we know about vorticity. If you stretch a column, so the isentropic surfaces move apart, delta H increases, zeta n must increase as well, so the circulation spins up. And if you tilt the isentropic surfaces, then the component of vorticity, the circulation, is just in that tilted direction. So all those things are easily in there. And this then dates back to Rossby, very much the way that Rossby thought about it. And the name potential vorticity actually goes back to Rossby. And it's slightly confusing because it suggests it's just a dynamical quantity. And as I've already described, there's as much thermodynamics in there as dynamics. And you could, the reason Rossby came up with this is just like potential temperature, you say, well, what would be the temperature of the air if I moved it from here to a standard level? Then this is, Rossby viewed this as the vorticity you would have if you moved the air to a certain latitude and gave it a standard height. Then what would the vorticity be? And so he called this the potential vorticity. Confusingly, the name is now used for this, or more exactly the differential quantity. If you multiply this by delta theta and go to the limit, then you have this as the conserved quantity on a fluid parcel, the potential vorticity. And Ertl derived this in mathematical form, and Rossby in this rather physical form here. So we have then that any function of the potential vorticity and the potential temperature is conserved in adiabatic frictionless motion. And if, in particular, PV itself would be conserved on a theta surface, and equally theta would be conserved on a PV surface. So we have those. But we can also easily think from this diagram what happens if we have frictional processes. If there's a torque changing the circulation, then that will change the potential vorticity. And equally, if there's a heating which is larger at one end than the other, it will change the length of the cylinder, and so it will change the potential vorticity. So you don't have to go to the complicated differential forms to see what is going to happen. It's all quite obvious there. So just continuing one more slide, then you can, as well as being conserved on a fluid parcel, you can invert the potential vorticity to get everything you want to know about a balanced flow. So you can get the velocity, the potential temperature, the pressure field, and you can even get the vertical motion as well from the potential vorticity, its distribution on theta surfaces, along with suitable boundary conditions. Now, just to put one little bit more of complexity in there, how much you get in terms of zeta, the circulation, and how much you get in terms of the change of height of a cylinder depends on the aspect ratio of the anomaly one's thinking about, compared with F over n, which is typically 1 in 100. So left to itself, the atmosphere always likes to equally partition, and it takes the natural ratio of scales, so H over L is the order of F over n. But if you go to the tropics, and the vertical scale is set by deep convection, then that means that this number, H over L, is a lot larger than F over n. And that means that most of the anomaly goes into the circulation in the tropics. So potential vorticity is really a surrogate for vorticity when you get to the tropics. But as you go to higher latitudes, then you get more this equipartition. Just another aspect of potential vorticity, the symmetric stability of a fluid. So if you have a motion in a direction, you're thinking about the stability which is to perturbations independent of that direction of flow, then the condition for instability is that F times P is less than 0. So in particular, if you have negative potential vorticity in the northern hemisphere, that situation is unstable. And if you make the hydrostatic approximation, the most unstable mode corresponds to inertial instability on an isentropic surface. So we will come across that situation later on. So the situation we have on our globe then is rotation in this direction of the globe. So a cylinder here in the northern hemisphere, where in the ambient we're thinking about a circulation this direction around the axis. However, in the southern hemisphere, this is theta plus delta theta, the circulation's in this sense. And that corresponds to those signs in potential vorticity. Now, if we go back to our Hadley circulation, there's no problem in angular momentum ideas if you move this air from here to here. But if you do that, you see the cylinder's actually upside down. If you're going to get the same sense of circulation as that, you have to flip it over, and that'd be gravitationally unstable. So you can't just move that cylinder from here to here and say, right, that's all it does. It's more than that, and that's what we're going to see. Going back still, I'm afraid a lot of this talk's going back to earlier papers, but This is from 1991, where I was concentrating on, well, one of the pictures I showed was this thing to do with the divisions of the atmosphere into 3 domains, which was building on work of others in oceanography and previously in atmospheric science. But there's the underworld where the isotopes, that's 270 Kelvin, are in contact with the surface. There's the middle world where the isotopes, there's 300 here, 330, 360, sorry, crossing the tropopause, which is this line here. So they're partly in the troposphere and partly in the stratosphere and can communicate between those 2 domains. And then there's the overworld where the isotopes are purely in the stratosphere, not crossing into the troposphere. So if we look at potential vorticity, the values typically in the stratosphere are 4 or more, whereas in the troposphere we might be thinking of 1 or less, and in the tropics maybe between 0 and 0.5 here. Now we're going to be thinking about the Hadley cell that sits in here, and thinking about the upper branch then, if we look along an isentropic surface, we'll be seeing the middle latitude and polar stratosphere here, with large values of potential vorticity. And if we look along here, we'll be looking at low values and in the tropical troposphere. And 360 is somewhere in the upper troposphere here, whereas the lower troposphere is more like 300, 305 down here. So we will be looking at isentropic surfaces and the potential vorticity moving on those. We'll also at one point just look at the potential vorticity equals 2, which is this line here, and watching the isotopes move up and down that as well. So we can use those 2 views of what goes on there. Right now, so to get back to the topic, if we, rather than look at the zonal average, we actually look at the still a time average for climatological July, but we now look in longitude. So this is longitude from 0 to 360, and this is 1,000 to 70 millibars here, and there's 3 isentropic surfaces I've put on there to orientate you where we were before. But the upper troposphere, something like 350 or so as the relevant surface here. Now, if we look at this, it's very clear that there isn't a uniform flow from one hemisphere to the other, quite the contrary. If we look in the lower troposphere here, we see a flow that's really quite structured. If we look in this region here, the Indian Ocean, there's the Somali jet here, just by the East African highlands that we'll look at again. There's a weakness here in the flow, and then wherever you get an island, then you get a strong flow. There's Sumatra, Borneo, and essentially the flow is strong by the side of all the topography and seems to use the topography to help get into the other hemisphere. Over Africa here we can see the flow into the northern hemisphere. Over the eastern Pacific and over the Atlantic, you see by the side of the Andes, then from there westwards, there's actually a strong cross-equatorial flow into the intertropical convergence zone that's north of the equator, and the same is true in the Atlantic. So that's the sort of structure at low levels, and in the upper troposphere then we do see reverse circulations corresponding to the Indian Ocean, corresponding to Africa, and the East Pacific and the Atlantic here. So there is a reverse circulation there. But I'll concentrate on the low levels to start with, seeing how the air gets from the southern hemisphere to the northern hemisphere in this northern hemisphere summer season. And this is again borrowing from previous work, Mark Rodwell's PhD thesis back in 1995. And we had a toy model of the Asian summer monsoon, which involved switching the heating on and then watching how the flow developed. And after 10 days or so, 7 to 15 days, you saw the tropical circulation develop. And the flow was quite realistic, coming across the Indian Ocean on a low isentropic surface into the northern hemisphere. Looks as if it wants to avoid India, but doesn't quite, perhaps, and then into Southeast Asia. And the lines here, which don't show too well, I couldn't resurrect this now, it's long lost data now, but the 0 PV line is here. So that's 0. So the 0 line has been taken way into the northern hemisphere. And as Peter Webster and others and us have discussed, the Somali jet is really inertially unstable almost. It goes down the pressure gradient, accelerates in this very strong flow here. But the potential vorticity does change following the fluid and eventually achieves northern hemisphere ambient values. And that appears to be due to some of the diabatic processes over the ocean here, but also the frictional processes by the East African highlands and also the surface friction. If you look at trajectories, then you see these trajectories, some of them avoiding India, others not, looking as they want to recurve, but then going into Southeast Asia. But being a toy model, you can play games with this, and if you increase the drag over the ocean, then the air is assimilated quicker into the northern hemisphere, and it avoids India completely. So the trajectories look like this. And if you decrease the potential vorticity sources and sinks over the Indian Ocean, then it keeps its southern hemisphere value, and some of it actually returns inertially back to the southern hemisphere. So this thing of avoiding India is not being unkind to India, it's just the air finds it very difficult to stay in the northern hemisphere. And indeed, the weakness of the flow, cross-equatorial flow, somewhere around here that I pointed to before, is again evidence of this almost coming back to the southern hemisphere. So the sources and sinks of PV are very important, and using all the friction you can, especially associated with topography. Now, if we look at, do a Hofmiller diagram, this is longitude from 0 to 360, and this is from the 1st of June to the 31st of August, and this is 2009. And so this is the Somali, the cross-equatorial flow, the Somali jet there, and you can see it fluctuates. There does seem to be something of a diurnal cycle in it, but there are also fluctuations, some fluctuations associated with propagating waves, as we see here. This is the bits between the islands here. If you want to see propagating waves, though, you certainly look at the East Pacific region and the Atlantic. The Atlantic from the high topography over Africa, and here from the Andes in the East Pacific. And you can see that far from being a uniform cross-equatorial flow, it's one that occurs associated with propagating waves as they propagate westwards from the topography and outwards. So we see this as very much transient features and essentially synoptic features and associated with those waves as they pass through. So that's what's happening at low levels, and we do have all that topography to help and all those processes that can go on. But what about in the upper troposphere here? There's no East African highlands to hang on to, so how does the air get across the equator in this? So that's what we're going to look at next. And to start with, I'll look at 250 millibars, which is a very suitable surface for the East Pacific and the outflow of the East Pacific and the Atlantic region, and it catches the bottom of the Hadley Cell bit for the Indian Ocean. And again, you can see there's a lot of structure here. Some of it seems to be associated with westward propagating waves, but even some with eastward propagating waves here. But certainly later in the season, it seems to settle into these eastward propagating waves. And most of the time in the Indian Ocean, the cross-equatorial flow is associated with those systems there. And if we want to see the Indian Ocean better, we go to 150 millibars, where you can see these are values sort of up to 25 meters per second cross-equatorial flow occurring in these bursts in this Indian Ocean here. So this is what the Hadley Cell looks like on a day-to-day basis. This is the cross-equatorial flow happening in a big way. So let's look at that a little bit more, and I'm going to show some pictures from the Indian Ocean region, the Asian summer monsoon to start with, for 2009. And we're going to look on the 370 Kelvin surface, which is quite high up. It's at the sort of the upper bit of the outflow of the Indian monsoon region there, the Indian Ocean return Hadley Cell branch. Now, if we look at the average for June, July, August, you see, depending on the color code, but here we see low values of potential vorticity in in and to the west of the big deep heating region over Asia. So this is the low PV being created above the heating and propagating westwards as a sort of Rossby wave, and even sometimes splitting in two because it feels like a PV strip, but that's another story. But we've got this anticyclone here, and this induces a circulation around, and that pulls high potential vorticity from the polar region right through south of the monsoon region and in a strip to the south there. So we get very high values pulled around there. My comment is, with a different color scheme, we should call this really the great red spot of the Earth. This is it. If you looked from Jupiter, you'd say, my goodness, look at the yellow spot on Earth. So that's what we're looking at here, and then these are southern hemisphere values here. But that's what it looks like in the average for the season. But what about one day? So this is what it looks like on one day. A lot of structure in this high PV being brought down to the south here. But then, interestingly, we see the signs of these events. You can see the cross-equatorial flow. These yellow values are northern hemisphere values coming in here. These are northern hemisphere values coming in and actually forming streamers that come right down, some of them right into the linking with the southern hemisphere synoptic systems, the troughs and ridges in the southern hemisphere, and strengthening the anticyclonic side of the southern hemisphere jet. Others get mixed in with the ambient PV in the region here and create smaller valued southern hemisphere PV in this region. So we see these streamers being pulled off, and this is what the Hadley cell actually looks like, the upper branch of these streamers here. Now, I did have a movie film of this, but it was going to be too complicated to make it work here, so I'm going to show you a different one now, which actually is a poor man's movie film in that's just run on the computer. What I'm going to do shows now is from the whole wave from 0 to 360. And it's going to show both 370 Kelvin and 350 Kelvin. And it's going to be for July 2008. So it's a year earlier, and it's July rather than this August season here. Now, take a bit of orientating. So just before I do that, sorry, I forgot I put this in. This links then, we think, with some of the equatorial waves that we've been looking at, Yang Guiying and I've been looking at in recent years, where we've been looking either taking measures of convection, this is brightness, temperature, and looking at the waves that go, the structures that go with that, or looking at the dynamical fields and looking at the convection that goes with that. But this is actually a structure that says, well, what do we see in both brightness, temperature, and in the velocity fields, when we have convection, a maximum, as given by brightness, temperature, in this region here. And this is the structure of the enhanced convection and the depleted convection on either side. And then this is the structure of the flow we see. And this is at 850 hectopascals and 150 hectopascals. And what we see at low levels is sort of Rossby wave structure in the off-equatorial region here, but still an equatorial wave, Rossby wave in the northern hemisphere. And in the upper troposphere, we see something really rather different. But if you look at this in time, what happens is that we see this low-level Rossby wave structure, which seems to organize the convection. The convection flares, and then you get this outburst from the top of the convection across the equator. And you can interpret that as a mixed Rossby gravity wave response to the Rossby wave and the convection occurring. So you get this outburst here, and there's some return flow here. So this is what we think is happening in those cross-equatorial flows and leading to those streamers that enter the southern hemisphere. If you use your near-equatorial convection as the organizing structure, then you get a very similar thing with, again, a Rossby wave and this mixed Rossby gravity wave, this cross-equatorial flow that we think we see the signs of in these fields. So now to move to that movie film, and this is then 370, this is 0 to 360, and this is a layer we looked at before, and the color scheme is not quite so good here for showing it, but you do see these things coming across here, and there's elements of those coming into the subtropical flow here. But I'm going to concentrate on the 350 Kelvin surface. These are very good. If you're suffering from jet lag, by the way, I recommend these. You can look at these for not too long, just for half an hour, and then you'll be asleep. So, so this is 350 here, and you see lots of structure here with the streamers coming across the equator, coming into the subtropical jet here. But I want to, and you see those happening all the time here, and equally in the, there's structures in the East Pacific too here, where you see these waves coming across here, and again, streamers getting pulled out, and similarly in the Atlantic. So this is the sort of cross-equatorial flow, taking its northern hemisphere PV with it, but then getting mixed in the, somewhere in the subtropics, or even getting to the subtropical systems themselves. And if those phase in with a trough like this, then they really tend to sort of almost reinforce that trough. So you see these here finishing up over Australia, and no doubt sharpening the jet there. But if the wave's gone by, then actually they tend to just get mixed in this region here. So it's very much a tropical, extratropical interaction, which these are almost passive tracers, which then go to amplify the southern hemisphere structures if they reach the right phase or get mixed in. Right, so that's something of June, July, August. I put in a structure here that we think is what's going on in the East Pacific or the Atlantic, where again we have, it's a more barotropic structure to the wave in the Atlantic, because most of them are triggered from upper levels, from higher latitudes. And the convection is organized differently, and the cross-equatorial flow is organized differently. But again, it's associated with the equatorial waves that we've looked at in other contexts. But now, so June, July, August were complicated, but if you're still with me, it gets worse. So this is now January, and do we just see the opposite in January of what we saw in July? Well, to a certain extent that's true, so let's concentrate on the bits that are easy to start with. So if you look at low levels in the Indian Ocean, you just see the reverse here. And to a certain extent in the upper troposphere over Africa and the Indian Ocean, you see the reverse. Now, the intertropical convergence zones don't move south of the equator in this season, they stay north of the equator. And we still keep the flow across the equator into the northern hemisphere. So that signature did not reverse because the ITCZ has stayed north of the equator. But we think we understand that. But then the more interesting structure here, this is the South Pacific convergence zone here. And here you see this, something that's not in this season at all. This sort of, well, I'm always saying waves everywhere, but I think you can see a wave there, can't you? This is the region of westerlies on the equator, and so is this. And Holton and Webster, ourselves, we've looked at middle latitude systems, subtropical systems, propagating into this westerly duct region and affecting the tropics. But what we have here is something a little different from that. We have what I think we can interpret as a mixed Rossby gravity wave that left to itself would propagate to the west. But because of the westerly flow, you can get a stationary response in that mixed Rossby gravity wave. And we see this then as a downstream response to the South Pacific convergence zone. The group velocity is in that direction. And so this we see as being forced by the South Pacific convergence zone here. And equally in the Atlantic, the same thing for the South American heating forming a downstream wave trend. You can see it propagating both eastwards and also upwards and downwards as it propagates. So those waves propagating there. So we see a mixture, and I'll tend to concentrate on that in the final bit I'm showing now, which is this picture here, again 370 and 350, and there's interesting structure on here, but I'm going to concentrate on this 350 surface here. And for this season, we're tending to see air coming from the southern hemisphere into the northern hemisphere. Over Africa, it seems to be more of a continuous stream of the air coming in here and strengthening the subtropical jet in this region here. And equally over the warm pool region here, you can see sort of tends to be a stream a streamer-type pattern coming into the northern hemisphere here. But I'm interested in this structure here. Here we're going to see a time when the South Pacific convergence zone strengthens. Then downstream from that, we see this strengthen here. So, and then following that, we see this strengthen here. So this is the eastward group velocity of a mixed Rossby gravity wave. And then it reaches the ends of the westerlies, and you get this sort of thin structure here. But as it propagates into the upper troposphere, then you see to the west, you see this streamer being pulled out in this direction, and this streamer being pulled out into the northern hemisphere. And this is about the 19th of January now. And this streamer comes right into the North Atlantic here, right across into the North Atlantic. So this is southern hemisphere air, still with its undiluted signature, right into the North Atlantic. And in fact, this process continues, and you have this beautiful streamer here. And before the end of the month, then we'll see this actually happen again with, again, this tongue here develops, and the sort of, you get a stream into the southern hemisphere here and into the northern hemisphere here. So again, the two hemispheres communicating with in this region here. So we think we're seeing a mixed Rossby gravity wave that gives a stationary, steady structure, but as the South Pacific convergence zone fluctuates, so you get this fluctuating behavior and these streamers being given off into the two hemispheres. Now, I said that I told you that date, the 19th of January, and I want to now look at yet another picture of a moving thing. This is now going to be, I'll warn you, but perhaps I'll put it there and I'll tell you about it while it's there. So don't worry about what it's doing yet, just where we are. And I'm afraid it's a picture from me, so there's the UK, but this is the Greenwich Meridian here. This is North America over here. This is the pole, and we're down to close to the equator here. This is theta on PV2 now. So this is, if you like, this is the motion on the dynamical tropopause. And this is the high latitude flow undulating here, and the interactions with the lower latitudes. But now if we look at this, it's starting on the 18th, and I'll run it a couple of times, but what we see is this very strong progress of flow into the North Atlantic region here. And that happens on this period here. So it's going to be 1 week. It starts on the 18th, and this is this region here that propagates into the North Atlantic and out towards the UK here. And if we see the change in the flow, from the 18th to 20th of January, it looked like this, the 250 millibar jet. And from the 21st to 23rd of January, it looked like this. Now, I haven't proved to you that streamer that came from the southern hemisphere at the end of that breaking mixed Rossby gravity wave actually induced this, but I think it's pretty sure it helped. So that brings me towards the end of my story now. So the Hadley cell is terrible, isn't it? You thought you had something that's simple and you could just say, well, that's what it looks like. And someone comes along and tells us, well, it's not quite that simple, but I think we need to know. So it's generally very localized in longitude and time. A lot of the flow across the equator happening associated with synoptic timescale systems, equatorial waves, and in streamers. So the lower troposphere, these sources and sinks are crucial. This is nothing against the UK Met Office, but it brought a smile to my face, I must admit, that when they put all the best ingredients together for their new model, it didn't rain over India. Now, you can turn all the knobs you like over India and try and get the soil moisture changing, but my guess would be there's something wrong in terms of the PV sources and sinks. So you need a bit of sort of understanding of the situation to actually know what the problem might be. So I think it's important to know this sort of thing. In the upper troposphere, you don't have the topography to help, and you then have to use these so you get these streamers and filaments moving to the other hemisphere where they mix, and they can strengthen the subtropical jet, and they provide a southward flux of PV. They provide that damping, if you like. As they mix in, they tell you just how strong that subtropical jet is going to be. The extent of that mixing is crucial. And the mixed Rossby gravity waves are important both for the steady structure and for all the transient systems, many of the transient systems. So a couple of questions then. How well is the era 40 data representing this, or era interim? Well, we don't know. It would be nice to actually verify some of this, and I think perhaps I'd look to the atmospheric chemist to help me here, because if you're taking undiluted air from one hemisphere to the other, one ought to be able to see that. How well is it represented in models? These are very shallow structures. They're associated with equatorial waves that are notoriously badly represented in models. We haven't looked yet, but I intend to. Is it important for weather? In the tropics, perhaps. Some of the structures that I've talked about are important. And for the middle latitudes, I've suggested it's important there. And for the interaction of the tropics and the extratropics, I think it is. Is it important for climate? Well, if it's important for weather, it's important for climate, in my book. But also the nature of the Hadley cell, I think it is important to know just what processes are really producing this reduction below angular momentum conservation. And this is what's going on, these streamers here. And I think we can represent things pretty well, but if you go to an aquaplanet experiment for a very simple control with zonal SSTs, then the models produced all sorts of different equatorial waves. Every model was different from every other. And if you look at the Hadley cell in this very simple situation, then there's about, the standard deviation is about 1 meter per second, and the average about 4 meters per second. So there's a lot of variability in the Hadley cells represented in these models. And maybe it's because they're representing these features in different ways. So is it important for atmospheric chemistry? Again, if you move undiluted air from one hemisphere to another in this manner, I think that's got to be important. And finally, I come to PV diagnostics are actually not just for extratropical people, they're for tropical people as well, and for those who want to see how the tropics and interact with the extratropics and the two hemispheres interact with one another. So thank you.
So we do have some time for questions, and I would ask that you go to the microphones. I do have a question. Oh, there is somebody there? Ah, yes, okay.
Hi, John Bates with NOAA.
My name is Yamanaka.
Looking at your, I'm sorry?
My name is Yamanaka from Japan.
Okay.
Probably you
I'll
can
answer
hear
two
my-
at once, that's fine.
We have stereo questions. Okay. Go ahead, please.
Okay. And I'm sorry, I missed the earlier part of your lecture because my abstract is 8:50 is the beginning time. Sorry, but I think the northern hemisphere is originally a land hemisphere, and southern hemisphere is originally ocean dominant hemisphere. So, how to say this? A kind of monsoon-like circulation should be considered. So, of course, this should be represented by some waves, but normally we consider the monsoon-like structure between both hemispheres. Thank you.
I totally agree that the monsoons are incredibly important, and that's how I came across this in the first place, was trying to understand the Asian monsoon. So I hope, perhaps I mastered a little in this, but I agree it's very important to consider that, and these sorts of things I've been discussing in the context of the monsoons as well.
Ryan John Bates. Your streamers, I look at a lot of satellite imagery, and total precipitable water has these streamers that we're now referring to as atmospheric rivers. And it seems that perhaps the structures that you're looking at, when they interact with the intertropical convergence zone, may actually bring some of that moisture and force some of those so-called atmospheric rivers. Any thoughts on that?
Yes, I'd like to think you're right. It's certainly tantalizing. Where we see this behavior in particular is, say, in the East Pacific, where I describe the waves as being sort of barotropic in structure. So the sort of behaviors I'm looking at in the upper troposphere would be mirrored through some depth. And whether that depth is sufficient to take the moisture into what we call atmospheric rivers, I don't know at this time, but it'd be very interesting to try and fit them together.
Brian, I have a very similar question to the one just asked. And could there be regions where there actually is increasing depth in transport? In other words, what's the variance about the depth of these streamers? There might be conditions on one end of the PDF where you can connect down to moisture feeds in the deep tropics. And also related to that, that example you showed there from 2008 that affected the UK, that looked like basically the generation of a very strong positive NAO type signature. So to what extent are these kinds of streamers, for example, perhaps important in large-scale regime changes?
Taking the latter thing, yes. I mean, I've always sought what is the ingredient one should put in for regime changes, and you know, ECMWF have used these rapidly growing middle latitude baroclinic wave type things as their ensemble generator in the past. Whereas really, if you want the change of regime, I've always felt it was the tropics that might give that unexpected change of regime. So that's the sort of catalyst I will be looking to see whether it actually does behave in that manner. Sorry, I can't remember the first part now. God. What was the first part then? Oh, the depth, yeah. So typically, as these things come out of the tropics, they would tend to extend in depth, I think, as they would interact with deeper flows of the atmosphere. So the characteristic height scale would actually tend to become deeper, I think, as that came into middle latitudes. But how much they deepen, I don't know at this time.
Hi. Question here. Here. I think this question may be related to the first one. I was just wondering, when you put in this cross-equatorial flow in the sense of PV source and sink for the Asian monsoon, so you had this very interesting experiment where you change friction and it avoids the Indian subcontinent, the flow is not flowing over, so basically kill the monsoon. So I wonder if you could sort of put in, Asian monsoon in a different light in terms of PV source and sink. So what is the cause of the monsoon going over the land? Is it because of friction? Because we usually think of land-sea contrast being the driver of Asian monsoon.
Thank you for the question. Yes, I mean, I think this bears on even wider in terms of how much is the Hadley Cell very much part of the global system, and the horizontal structures I've been looking at, it doesn't really matter too much, it would happen anyway, or how much do they actually feed into what that structure can actually be. And I'm not sure we can put our hands on our hearts and say we know the answer to that. I believe we can reach a certain level of goodness of simulation, etc., without considering these sorts of things, but maybe to go beyond that, we really have to consider how these structures behave. And the sources and sinks of PV, to a certain extent, maybe they have to be like they do, but that's not true, because we actually put the heating in the monsoon region, and then the flow is inconsistent with that. So I think there is an interesting balance between the sort of drivers of these land-ocean contrasts and the structures which enable them to happen.
Just 1 second. Can I follow up on that question? Because there's a marvelous paper by Alan Plum and Henry Ho, and just talks about how difficult it is to have a subtropical meridional circulation driven by heating. It has to be very, very strong heating. Which brings me back to your question about the Himalayas, this enormous potential vorticity minimum. Yep. What can you say about that?
It's beautiful.
It's beautiful. The yellow spot.
Yeah, I mean, it is a fundamental part of the circulation of that. I mean, it's that actually, as it drifts westwards, the circulation around that then gives the mid-Pacific trough. And it's then determining the whole structure in that region as it spreads over West Africa as well, very much there. So, I mean, I think it is hugely important there.
In one of your summaries, you mentioned that PV is important to atmospheric chemistry. And I'm very anxious to ask you in what context that is important. in terms of chemical reactions, in terms of transport, or in terms of formation of aerosol?
Well, I brought this here to give over to those who know far more about it than I do. And so I was hoping someone would come to me after and say, ah, yes. But to me, it is extremely important if the transfer of mass from one hemisphere to the other happens in a fairly dilute, uniform manner, or if it happens in very concentrated filaments. That must be important to the chemistry. After that, it's over to you.
Question.
Yeah, this might be a more tenuous connection, but thinking about cold surges into the tropics, which I guess tend to be relatively rare in space and time. I mean, we might think those will tend, you need to have a cold landmass and a pathway for that air to make its way without mountains or water covering them to the tropics. But I wonder if there also could be an element in what you've been describing today that could help drive some of those cold surges into tropical regions.
It's an interesting thought again. It's great to give a talk because you get all these interesting ideas, and whether a cold surge is more successful if it actually phases into something that the tropics wants to do is an interesting question.